Yeah. Good afternoon or good evening. So it's 7 o'clock here in Germany. So it's quite late for the presentation. So let's get going. Um, as Jamie has already announced, I will be talking about calibrating machine learning prediction models. And before I can really start with the topic, I would like to thank several people. I've marked two in orange in our cardio care orange. Yao Hu, she has done all the real data analysis, and Francisco Ojeda, he has done all the simulation studies, and you can see a few more people listed there, including two clinicians who helped us with the real data. This figure here should illustrate the main problem. So this is from an illustration I will show later in some detail. What you can see here in this figure is a predicted probability on the x-axis and an observed proportion on the y-axis. And in fact, if you have observations, then they should just be on this diagonal line, so the solid black line that you can clearly see. But in our two data sets, we have some kind of overestimation of these probabilities, both in an external validation data set and a temporal validation data set. So you can see a clear deviation from this straight line. And this has happened because we haven't done any calibration with these data when we generated this plot. So please think about the use of calibration when you analyze your data. And if you do this kind of proper calibration, this figure here shows the no calibration plot that you've seen before on the left. If you do logistic calibration and if you do some kind of refitting on your validation data, then you can see either with a standard logistic calibration, which I will explain in a few minutes in detail, and some other calibration methods as well as refit of the data might be helpful to improve the model fit. And actually, if you want to predict probabilities, this might be the right way to go. So either do a calibration or a refit, depending on some factors that I will discuss after having shown the simulation study. So if I want to phrase my problem in a few words, then I can clearly say, okay, I want to estimate a probability machine. And assume now I have developed this probability machine on training data. A probability machine is nothing else but just maybe a logistic regression, so that you just estimate the probability from a logistic regression model. It could well be something different, that you say you're using a random forest in a probability estimation mode, or you are using gradient boosting on dichotomous outcomes and are actually able to estimate probabilities. You can estimate probabilities from support vector machines, and there are a whole bunch of other machine learning methods that can be used. So now assume that you have used your machine on your training data and you've developed your probability machine. And then the aim is, and this is the main issue here, you want to apply this probability machine to new data from a validation population. And if I now transfer this into some kind of simple application problem, then my example is, okay, maybe the problem in the first run is I want to estimate the probability of a myocardial infarction at the emergency department. And I assume now that this has been developed using a probability machine using cohort data from a specific clinic. And now in the next step, I really want to apply this to new patients from a new clinic. So cohort data are available for patients at Clinic B. And should I just straightforward apply the model developed from A? And I can already say, no, that's a bad idea. You should, in most cases, do a proper calibration of your model. Why have we looked at this problem in some detail? Well, we published a special issue in the Biometrical Journal about 7 years ago on probability estimation and machine learning. And you can find in our initial paper, on one of our papers we published there, the following paragraph. which is given in this box. And I've specifically marked one sentence which we wrote there. It is unclear how machine learning approaches can be calibrated. So it was clear, absolutely straightforward how a logistic regression model can be calibrated. And for some of the machine learning approaches, it was also quite clear how this could be done. But we were lacking at that time a clear understanding of how could it be done. And we had discussion papers in this special issue and also some reply. And after that, I got a reply by Charles Elkan, and he sent me one of his papers in which he proposed a very nice and very simple calibration approach. And this actually was the starting point then to investigate the literature. And after 7 years now, we have done some simulation studies and some additional analysis, and this is what I would like to show you today. So the outline is very simple. I've tried to sketch the calibration problem in the previous slides. Now I want to move on to the various calibration approaches that have been proposed in the literature. I would like to show you the setup of our simulation study and some results from these simulations. And then I would like to take you to two real data analysis. The first data set is from the University of California in Irvine machine learning data repository. It's the standard Cleveland Clinic data. So it's on the diagnosis of coronary artery disease in a non-invasive way. And the second example is from Germany. It's from the German stroke study calibration. And there we want to predict outcome 90 days after an acute ischemic stroke. And here we want to obtain two models. One is for complete restitution, which is functional independence after 90 days. This basically means that a patient can walk by himself, can feed himself, can brush teeth independently, and so on. So it's something about activities of daily living that are measured there. And this is what we want to see, whether a patient suffering from a stroke or having experienced a stroke is functionally independent. This is one of the outcomes, and the other outcome is that we want to look at mortality. About 10% of the patients reaching the hospital die within the first 90 days. So this slide here seems to be a little bit busy, but it just describes in a very simple way the very general algorithm how you can calibrate your data. And maybe some of you ask yourself, why is he showing this slide? Well, it took me quite some time to really understand what is calibration about, how can it be done, how can it be technically solved, and this simple algorithm given in some words and definitely more than 7 lines and 7 words per line shows how it can be done. So here, step 1 is that we develop a probability machine, and this is called probability machine 1 on our training data. And in step 2, we want to we apply actually this probability machine 1 to our validation data. So we do the development first, and then we actually apply this machine to the validation data. This then leads to the figure, or this kind of figure I showed you at the very beginning of my presentation, where we had this clear deviation from the 45-degree angle. And therefore, we now start with the calibration procedure. And for this, we estimate a second probability machine with the dependent variable, and that with the dependent variable that is the outcome from the validation data. So this is just the 0, 1 variable from the validation data. And the independent variable is just the linear predictor estimated from step 2, or the estimated probabilities from step 2. So you have a simple dependent variable, which is a 0, 1 variable, and you have a simple independent variable, which is either the linear predictor or the estimated probability. So you have a new data matrix with a Y and an X, and then of course you can run any machine on this that you would like to use. Now assume that you've trained this second probability machine in step 3, then you can apply this machine to a new observation in the following way. You first apply the first probability machine, store the linear predictor or the estimated probability, whatever is your basic outcome from your probability machine 1. And then you apply probability machine 2 using the estimated linear predictor, estimated probability, and then you have your calibrated probability. And this is just the probability estimate from the second probability machine. So it's very simple. You just run 2 probability machines. That's all what you do in calibration. And this very general algorithm already makes clear that you can use a whole bunch of different approaches for calibration. And the traditional approach, of course, is regression-based calibration. So in this case, this goes back to Sir David Cox in the late 50s, and that's a paper in Biometrica. So it's a very old concept. So you use your outcome yi in the validation data. You have estimated your probability using probability machine 1 or just the probability machine from the training data. And this estimate, when applied to the validation data, is this pi I hat, which is given in the second line here. Now you perform a regression of yi on this estimated probability or its linear predictor, which I typically call eta I hat. And then you have this functional form given in equation 1. And of course, f is a standard cumulative distribution function. So this is what we learned when we were talking about generalized linear models, and specifically logistic and regression and probit regression and so on. And you can choose, sorry, excuse me, any cumulative distribution function for this. And then you just obtain the calibrated probability as the fit from this simple regression model. And what is important if you do it with a logistic regression with one intercept and one slope as given in equation 1 is that this logistic calibration can be shown to be optimal for different probability distributions. And even the conditions for this optimality have been formulated. And you can find this in a very nice paper, which was published this February by Böken. So one of these regression-based calibration approaches is logistic calibration, repeated here in the first line. The most prominent approach for calibration used by machine learners. So when you go to some of the conference papers and so on, there you can find the Platt scaling. And what is Platt scaling? Well, some people say it is equivalent to logistic calibration. In my opinion, it's different. So Platt scaling was proposed, and I give the reference at the bottom of the slide in a chapter. Platt actually used the output from a support vector machine and fed this output into some kind of logistic regression model. And therefore, I personally interpret Platt scaling as some kind of logistic calibration where you use the non-transformed estimate. And therefore, in our simulations and also in our writing, we make a clear distinction between logistic calibration, where you always use the linear predictor to be fed in, as you can see in the first line, and Platt scaling, where we use the non-transformed estimate, which could be the estimated probability, or it could be a linear predictor. So later, when I talk about the simulation study, when we talk about Platt scaling, then it's in fact the estimated probability, and logistic calibration then is that with a linear predictor. When you start with logistic calibration, you can use some or derive some other special cases. Slope calibration has been proposed by Cox as well. There you just ignore the alpha from the first line. Intercept calibration, there you drop the beta. So the eta I hat is just used as an offset in an intercept-only logistic regression. And these are the two very simple variations of this. Sometimes you can find the term sigmoid calibration and logistic calibration is termed or used synonymously with sigmoid calibration, but actually sigmoid calibration could be based on any sigmoid function, so any reasonable cumulative distribution function. So this is somewhat wider in my interpretation and in our interpretation compared to standard logistic calibration. Then there's another approach also based on logistic regression, very similar to original logistic calibration. And this was proposed quite recently in that paper by Kuhl 2017 in the Electronic Journal of Statistics. It's the second reference I give below. And in better calibration, you do something like a two-component logistic calibration where you explicitly model the pi hat and the 1 minus pi hat. And so you estimate 3 parameters in total rather than 2 as in the original logistic calibration. It has already been shown in the Kuhl paper, and it has also been shown in the Birken paper that better calibration and logistic calibration are equivalent, and the conditions for this equivalence have also been formulated. But when you recall this very general algorithm that I described a few minutes before, any regression-based calibration approach could be used. This could be a local regression, such as local logistic regression, but there are other approaches available. The disadvantage of most of these approaches is that they are not available in standard software. One of the recent papers that has used such a local regression approach is the Dorman paper from 2020, which is given as third reference in the bottom line here. You can easily combine regression-based calibration with some ensembles. So you could use some kind of regression-based boosting or some kind of bootstrapping. I think there are a whole bunch of variations available. Some specific regression-based methods have been developed, and I've provided 2 examples. One is the random forest-based calibration approach we published 5 years back in time, and the other one is the logistic model trees for construction of probabilities in random forest, and it's also given in one of the references at the bottom. Now, so this was just about regression, and now this was clearly parametric regression, but are there non-parametric approaches? Yes, there are. And one of the standard parametric, non-parametric approaches is isotonic calibration, and this approach seems to be loved by the machine learning communities. In fact, what you get at the end of the day, if you use this approach, isotonic calibration, is a step function. So it is truly with discrete probabilities. So it's not a continuum anymore. And I have an example on the next slides so that you will see that truly a step function is constructed when you use this approach. And depending on the discreteness and the size of your data, the step function can be quite discrete and have just very few values. You will see this when I move on to the example. You generate monotonically increasing values on the estimates. The theory of isotonic calibration has been nicely described in the paper by De Leo in the Journal of Statistical Software about 12 years back in time. And De Leo et al., they described 2 algorithms in detail. One is the so-called PAVA, or sometimes just PAV algorithm, which is a pooled adjacent violator algorithm. And the alternative is the ASA, not the American Statistical Association, but the active set algorithm. And I will describe the PAVA in some details on the next slides. It's equivalent to the the rock convex hull approach. I've provided the reference, and it's essentially a non-parametric estimate of the rock curve, and it's nicely implemented in the ISOREC package by De Leo et al. So how is this PAVA actually working? in this toy example, you see I have generated 10 subjects, and we have our linear predictor. And what I've done is that I've ordered the linear predictor from the highest value, first row, to the lowest value, last row. And you can see that we have our outcome values 0 or 1 for each observation here. And what you can see here is when you look at rows 8 and 9, then you can see that we have a non-monotone pattern. So when we have the lowest linear predictor and an outcome of 0, that's fine. But if we have a linear predictor of 0.25 and an outcome of 1, then of course we should have an even higher outcome to have some kind of monotonic pattern if we have a higher linear predictor, and this assumption is clearly violated. And what the power does is actually it takes the average of the two values where you first observe this violation of the monotonicity. So in this case, we select the 0 and the 1, and we take the average. But then in the next step, or for the next step, you can see this 0 here for subject number 1 has an outcome of 0. And this clearly is lower than the half, which is the average from the subject 7 and 5. So we need to average these as well. And of course, the average then is a third. And you can see now we have a monotonicity here for the first 5 observations, starting from 0 to 1. But for subjects 6 and 7, you can see that this monotonicity is violated. So we have a 1 and a 0, so we need to average them. So step 3 is the average with a half. And then we can see now we have a violation of the monotonicity here as well. And the average of these 3 values is then 2/3. Then we can see, okay, with this one, we have another violation and we need to average this. So the final ordering now without any violation of the monotonicity assumption is this given in step 5. So this is how the algorithm is actually working. There are some other of these binning approaches or non-parametric calibration approaches. One of these is called binning averaging. It was proposed by Zadrozny and Elkan in 2001. It is also termed binning quantiles. And this is very similar to what we know from estimating class probabilities in tree-based methods. So we actually order our observations from our validation data by the estimated probabilities, and then we divide them in a small number of bins. And I've specifically mentioned what Zadrozny and Elkan have done in 2001. They just used 10 bins. And this means at the end of the day, you just get 10 different probabilities in your validation data, because the calibrated probabilities just equal the averages over the probability estimates per bin. So this is a very crude, a very rough approach. One of the clear disadvantages has already been mentioned. It is the limited number of bins. They use 10, so you just get 10 different probability estimates, even for a large data set, maybe with 100,000 of subjects. And within a bin, the probability estimates are constant. So this is definitely not my preferred approach. But of course, you can combine this approach with any kind of ensemble method. So rather than using a tree or this kind of binning averaging approach, you could clearly embed it into some kind of forest-based approach, either standard bagging, or you could easily include it in some kind of random forest approach. If you are interested in this, you can look at the paper by Birken. He has a very nice review of the different non-parametric approaches. This approach here seems to be a relatively new one, and sorry for the formula. I hope I can take you through this somewhat busy slide in 1 or 2 minutes. Actually, this approach was proposed in a paper by Chen Chen et al., they just gave the rough idea, didn't write down all the formula. And for estimation, they used a different approach than we did, but it provides a very nice and general concept. And later on, I typically refer to it as the likelihood ratio based approach for calibration, or a general updating approach according to Chen. So what we have in our data set is we have some kind of base rate for the initial data set, so for our training data. And for the test data, which I typically call validation data, we also have a base rate. And you can see that you can make the distinction, or I make the distinction here between the training data set and the validation data set by using the prime for the validation data. What we can now do is, once we have developed our probability machine, we can estimate when we apply our probability machine to our validation data, we can estimate these pi hats, and we can then estimate the density. So do something more complicated than just a histogram, just for the group of the cases. And we can also estimate the density just in the group of controls. And then we can form a likelihood ratio. And if we use this likelihood ratio and apply the base formula, then we end up with a very simple thing at the end of the day. So if we start with what we want, which is the probability in our validation data that a subject is affected, given our probability estimate pi hat, then we can apply the base formula and get this expression here. And if we now divide the numerator and the denominator by this f prime of pi hat given y equal to 0, then we just obtain this expression over here, where this p prime of y equal to 0 just is 1 minus p prime, and the other terms are explained in the very similar way. How does this work? I've used our stroke data to provide you with a simple illustration. So we have estimated the density for subjects who showed complete restitution 90 days after stroke, and those who either were functionally dependent, so incompletely restituted, or died. This is the red line over here. And what we can now do is we can take the likelihood ratio, and you can see that crossing point where we exactly have a value of 1. And this, in fact, is our likelihood ratio function. And then these values for an estimated probability or an estimated linear predictor can be plugged into the formula I showed you on the previous slide. There are other general updating approaches with a base formula. I can promise you I won't guide you through this slide here, but what you can see is this general updating approach by Elkan, proposed in 2001. Actually, this is the work he sent me after we published our paper in 2014. This ends up with a specific base formula where you see expressions that you have seen before with the base rates and the probabilities given some kind of covariance distribution. And this is a very simple approach to do it. And Elkan in his paper even provides the proof for the validity of this very unusual base formula. Other calibration approaches are available as well. And here on this slide, I just list 4 different papers, 2 by Bella. She has primarily been working on calibration. And then there are 2 quite recent reviews. One is the already mentioned paper by Birken, and another one is by Huang from published in JAMIA. I think these are 4 nice references that can be used as starting point if you want to dig into this area deeper. Now, if we want to compare machines, then of course we need to have measures to estimate the performance of the machine before we can do a comparison of several machines and different calibration approaches. And the first statement I would like to make is here we are interested in estimating probabilities. So the clear statement is if you do a classification and use the AUC, so the area under the curve and the ROC curve, so the receiver operating characteristic, then these are not deemed suitable in probability estimation problems. So the most commonly used approach, if you have theoretical probabilities available, is theoretical probabilities available as here is the mean square error. That's quite clear. The Breyer score, which goes back to a paper by Breyer from the 1950s, uses the observed values rather than the true probabilities, but in fact, it's also some kind of squared error type. There are other approaches to it, such as the log loss, and I've provided you with a formula here, and you can see it's some kind of entropy measurement. So this measurement is related to the Kalbeck-Leibler distance, and there are other loss functions. In the last line, I've mentioned the spherical loss function. And what is quite important, and this has been given in the paper by Knighting and Raftery in 2007, that all these different loss functions are proper, which actually means that the loss is minimal at the true value. And what has been shown quite recently is that any prediction algorithm that is optimal under the log loss is also optimal under the Breyer score and the spherical loss. And the reverse is not necessarily true. So we have decided to do the optimization for some of our machines using the log loss, and also to use the log loss as the preferred measure of evaluation rather than the Breyer score. And when you go back to our previous work on this topic and similar topics, we used the Breyer score because we were not aware of this relatively new result. Now we have the evaluation measures, so the losses, and how can you do the comparison of two machines if you have, let's say, two different calibration approaches? How can you judge whether one calibration approach is better than the other, or the one is non-inferior to the other, and so on? Then we have written a few words about this in a couple of papers, and I've provided you with 2 references on this topic. And just as a brief statement, we clearly recommend resampling to do it. We don't prefer the analytical approaches here because they sometimes have quite unusual properties. This is something we've observed primarily on simulated data. And we typically do a bootstrap to obtain confidence intervals for the difference of 2 of these performance measures. So maybe a confidence interval even to compare the log loss of 2 different machines. If you want to compare multiple machines, there are approaches available as well. And the approach we have used in our simulations and also in our real data analysis is an approach that is described in detail in the paper by Demshar from 2006 and the Journal of Machine Learning Research. Actually, he used C calibration approaches on M data sets, and he worked with a rank, and he actually took the average rank of the calibration approach, and with this he used some kind of modified Friedman test. In fact, it was the Eman and Davenport version of the Friedman test, and the test statistic is given just for sake of illustration here on this slide. And if you want to see a nice illustration, just go back to the Demshar paper. It provides you with all the necessary details. So the global null hypothesis of this test is that, let's say, the performance of all machines is identical. But if the global null hypothesis is rejected, you can proceed with a pairwise post hoc test. There are several approaches available for this as well, but we use the Nemenyi type of this post hoc test. For this, we calculated the so-called critical difference using the studentized range distribution. And since most of the papers just deal with some kind of tables, I wanted to let you know in R it's simply implemented. You just call Q2key, and what you need to know is, and this is not stated always, that you have to set the degrees of freedom to infinity, and then the whole procedure is working quite nicely. Now, after having described the methods, I talked about the performance measures and how to compare the machines. Now I'm at the stage that I can describe the simulation study in some detail. So what we did in our simulation study, which actually ran a couple of days on our cluster in Davos. Why did it run a couple of days? Because we generated a whole bunch of different models and did a reasonable number of repeats, but we didn't use optimized parallel coding. So it ran on a single node with 128 cores for something like 4 days. We will make all the code freely available, so you're more than free, and we would be happy if you are able to rerun the code and get the same results as us. So what we generated was, we generated data from 2 different populations. So one was the training population and one was the validation population. And of course, we used different disease prevalences. Otherwise, calibration is not necessary if everything is just identical. So we really used different disease prevalences. We did the model building. So the first probability machine was estimated on the first population. And we did something special. The second population was split into a training, which we call cal training data, and a test data set, cal test data, to have a true independent test data in the simulation study. In most scenarios, we use the standard logistic regression approach for data generation. Maybe this is the reason why logistic calibration is performing quite good, but this is what we have done. And this is what we've done in other simulation studies before. And we've sometimes seen that logistic regression is not the best approach in these cases. We wanted to study one model where we had clear non-linearities. Actually, it's some kind of circular model, or model with some kind of circles when you go to the densities. And this model is generally called the Mies model because it goes back to a paper by Mies and the JMLR from 2007. In general, in our simulations, the intercept was 0 for model building and it was 1 for calibration data. In general, continuous covariates were generated according to a standard normal, but we deviated from this in some of the simulation models. In general, we used uniform discrete random variables when we used discrete ones, and we used 100 replicates per scenario. How many scenarios did we look at? In fact, it was 18. And I can just guide you through this busy slide with the 18 different scenarios. So the first scenario is a relatively simple one where you have just 2 continuous covariates. The second one and the fourth one are these non-linear models where you have this kind of circular structure because data were generated under the Mies model. This is a hard to fit model if you don't explicitly include the important covariates. Model 3 has a smaller calibration data set for training. And then in models 5 to 11, you can see that we wanted to see the effect of different noise variables. So models 1 to 4 didn't have any noise variables, but here we have some kind of cropy variables that don't have an effect at all. And of course, the more noise variables you have, the harder the data should be fitted, or it should be harder to fit the data. And models 5 to 7 differ from models 8 to 11 by the fact that in the first case, we just use 2 continuous covariates, and otherwise we have a couple of categorical covariates, and some of the machines have issues in dealing with these models. Then models 12 to 16 have only a single continuous covariate, and what we did there was that we wanted to investigate if we change the variability of the covariate in our calibration data, what's the effect? What is the effect if we change the effect direction or the covariate distribution, that we have a shift and a change in the variability? And this is something we wanted to study in models 17 and 18 as well, with when we added some 10 noise variables to that. We did some kind of scoring, even by hand, for sake of comparison, and just to give you an impression of my own scoring, my handwritten scoring. I also have an electronic version of that, clearly. But what you can see here is that there is a clear difference in the pattern. So actually, when I did my scoring, I used scoring as good. So when I said my calibration, the calibration was doing nicely, and whether it was doing poorly. And you can see that for some of the machines, you don't find any marks, and then this was just an intermediate result. In our simulations, we were using 5 different machines. One was logistic regression, one was random forest, the third one was support vector machines, then it was a gradient boosting, and then we also used the elastic net. And what you see here is when you go and look at the bad plots, you can see that you have a lot of marks for all the machines at the no-cal. And you have similarly a lot of marks for the slope calibration. And you can also see that some of the machines failed completely, such as number 11, or we had bad results with number 10. And you can also see that number 2 and number 4 didn't have any machine where we obtained a good calibration. So what were these numbers 2 and 4? Number 2 was the Mies model. Number 4 was a Mies model where we had a smaller a smaller data set to train the calibration model. And numbers 10 and 11, let me go back 2 slides, please. Number 10 and 11 are those where you had a lot of noise variables and the model where you had a whole bunch of categorical covariates. So these models were hard to fit. And in general, when you look at the colors here at the left, you can see that only the green, the black, and the gray generally show up here. The black is the logistic regression. The green is the support vector machine, actually with a radial kernel, and the elastic net. So when we tried to fit all these different data, good calibration was only achieved for a small portion of the machines. The next general message is, of course, when you look at the column, which includes the refit of the data, which is given here in my handwriting, then you can see the refit didn't perform well, for instance, in this model 8 for 3 of the machines. It only performed quite good on logistic regression. But you can see that the refit performed well on some other machines, sorry, not the refit, but some other calibration approaches performed quite nicely in these simulation models here. So if I now move forward to some of the more formal evaluations rather than my scripts here or my scratches here, I've selected just a few results where I show you some of the scatter plots we obtained for predicted probabilities on the y-axis versus true probabilities on the x-axis. So here you see one specific scenario, which is scenario 15. So this is one of the scenarios where we had a single covariate, but we had a change in the regression coefficient. And what you can see here is that when you run a logistic regression on these data, you get completely different results compared to the results that you obtain when you run a support vector machine on these data. And in fact, there were 2-3 simulation scenarios in which we saw some kind of weird pattern when we were fitting the support vector machine. So the tuning probably was not able to capture this completely. What you can see here in the upper part, when you think about, okay, logistic regression was used as a basic machine, and then we did all the different calibration approaches. You see some kind of general pattern. The slope calibration was a bad idea here. In this case, LCAN calibration can't work properly because we have explicitly modeled a change in the covariate, and the LCAN general updating approach requires identical covariate systems. Here you can see this kind of effect of the monotonicity that you get, so of this kind of binning, that you typically have a wider variability in isotonic calibration. You can also see that logistic calibration, beta calibration, and in most cases intercept calibration perform very similarly. no calibration always is a bad idea. You can summarize this result by looking at the critical differences and plot here. And actually this figure tells you for scenario 15 something very similar. The best approach seems to be logistic calibration, and refit is very similar. So there's no significant difference between them. Intercept calibration is close, beta calibration is close, and all the other calibration approaches are definitely further away. And when you think about the support vector machine, look at these figures once again. Refit was doing incredibly well, and this actually turns out to be the best approach here. When you look at the critical difference, then next best was beta calibration. Logistic calibration forms a homogeneous subgroup, and all others are bad. So the results are, when you look at this machine-specific results, very similar. Now I want to show you the results for scenario 3 and for scenario 7 when we average the critical difference approach over all models. Scenario 3 is the model in which we have a smaller calibration data set at hand. And in this case, where we have a smaller calibration data set at hand, then refit should get a bigger problem, and this is seen here. So you can clearly see that refit is definitely not the best approach in this approach, because we didn't have any change in the covariate structure. Intercept calibration turned out to be the best one, and logistic calibration and LCAN calibration were next. As expected, plat calibration and beta calibration are somewhat in the same ballpark. So whenever you have a smaller calibration data set at hand, you really need to think about, am I on the right track if I want to calibrate the data by refitting the entire model? Here in scenario 17, we have an unequal covariate distribution, and what you can see if you run this model here, the LCAN approach is the worst you can do, and refit is doing quite nicely, and logistic calibration is also performing quite well. This is the main results from the simulations I wanted to show you. Now we can move on to the first illustration, which is going to be a relatively short one. It's the Cleveland Clinic data. The idea here is to diagnose coronary artery disease. The standard approach to do that diagnosis is by doing a coronary angiography. This is clearly the reference standard, but it's expensive. It has a small risk of complications and even death. And of course, it involves radiation exposure, but of course, it is the reference standard. But the question is, can we let's say, pre-select subjects for coronary angiography by some non-invasive testing. So this was the idea from the Cleveland Clinic project. The initial paper goes back to 1989 by Detrano et al. So our question here in this specific application is, can a probability machine accurately predict coronary artery disease? For the training data, we took the data, the 303 consecutively recruited patients from the Cleveland Clinic between May 81 and September 84. We had a couple of covariates available, and the validation data comprised 617 patients from 3 centers in total. The outcome variable was the diagnosis of coronary artery disease, determined by the presence or absence of at least 50% diameter in an angiography. And what I want to show you is some descriptive statistics here. We don't need to go look at these tables in some greater detail, but what you can see is that in the training data, we have about 46% subjects with a coronary artery disease as determined by coronary angiography. And you can see there's a substantial difference in the validation data. When you look at the age distribution, it's 54 mean age in the Cleveland Clinic data, and we have some variability here in the validation data. When you look at the sex ratio, it's about 1/3 females in the Cleveland data, but substantially fewer females in the validation data. So we have some covariate imbalance. So I expect that the Elkan approach doesn't perform well because this requires identical covariate distribution, for instance. This plot here shows you the main results from the logistic regression. The left column here is always the training data, and the right column is the validation data. Maybe you have seen the radar plots before in this way. The black point is the point estimate from the logistic regression. The blue point is the upper level of the confidence interval, and the red point is the lower level of the confidence interval. These four variables were significant in the model selection procedure on the training data, and you can see a very similar pattern on the validation data. All these variables were significant, even the max heart rate. The results here are the most important variables from random forest. Left training, right is validation. And you can see the blue point is actually some kind of effect estimate. It's a p-value indeed. And you can see this kind of reddish spotted line is the 5% line. So you can see some of these variables were significant at the 5% test level when we ran a random forest. And you can see a very similar pattern here in the validation data. So overall, I expect some kind of smooth results here. And when you do the calibration, it turned out as expected. The Elkan calibration, which is given here, is number 9. So next but last in the second row, shows some kind of deviation. Since we had some smaller data sets available, the refit had some issues over here. So when you just look at this simple example, even no calibration seems to perform better than the refit, but this has to do with this kind of unusual structure of the data. And logistic calibration actually outperforms the refit in this way. If you do this with the other machines, you can see the other machines don't regularly perform as well as logistic regression. You can see some kind of bump in the random forest. You can see that no calibration did not turn out nicely here. You can see on the support vector machine, the refit performs quite nicely. And of course, we have summarized these results not only in the critical differences, but here I want to show you the box plots for the log loss. And what you can see here is generally that a very good approach is the refit of the data in general, but there are a few outliers, especially for the random forest procedure here. And this is one of the take-home messages. So when you work with the Cleveland Clinic data, the structural differences were extremely pronounced. So either you have to run a refit, or you need to be very careful in your modeling of the data. For the stroke data, we created 2 models, as already announced about 40 minutes back in time. One was for functional independence, measured using the so-called Bartel index. So it was functional independence versus functional dependence or mortality. So this is our complete restitution model. And we looked at mortality versus survival. What is the strength of this data? We first estimated the probability machine using standard logistic regression and published this in 2002. And then once we had these training data, we did a sample size calculation for this test data using an approach which is very similar to the most very recently published sample size calculation approaches for validation studies. And then we actually, after that sample size calculation, started collecting data for the model validation. The training data were collected in 1998 and 1999, roughly 1,750 patients from 7 hospitals. The test data or the validation data were collected in 2001 and 2002, involving roughly 1,800 patients from 11 hospitals. When you look at the difference of the sexes, they are very similar. It's the age distribution which is similar as well. So the Elkan approach should be working here, and overall I would call this to be a very smooth data set for training the complete restitution data. When you look at one speciality of these data for the validation data or the test data, we had 11 hospitals. And what is marked here in blue are the hospitals that also participated in the first study when the training data were collected. So you can find Minden and Essen here, Harlaching and Großhadern, both are hospitals within Munich. And you can see that a whole bunch of other hospitals, so with a completely different population structure, participated in the validation study. Nevertheless, data are relatively smooth, so you can see some violation of this smoothness when you look at prior stroke. It's just 20% here, it's 23% over there. It's with diabetes prior to stroke, but this kind of imbalance is really modest. This is the plot as before. We don't need to look into this in some detail. What you can see here is this is for the complete restitution model, the fits from the logistic regression. The pattern is very similar, so you don't see a big change in this kind of circular or this kind of net structure over here. And when you look at the results from the random forest, the p-value based results, and the same pattern here, you can see that in general the pattern is very similar. You see that there are some important variables in both of the test data sets or validation data sets, and you can see that a few more variables are important here in the training data. And one of these is artery location. And there's one important aspect that I would like to mention when you look at these figures, and I'm pretty sure you can't read all the letters that are given here. But what you can see here up there is that there are just two paresis variables in the model. There's the right arm paresis given up here and the left arm paresis given down here. While when you run the random forest, you see the right leg paresis, the right arm paresis. You can see the left leg paresis and the left arm paresis. And this is because the models are actually operating in a completely different mode, and multicollinearity doesn't affect random forest. And this is one of the strengths, I think. When you look at the plots here, you can see the refit, and you can see that the refit is doing quite well on the random forest, and you can see that the refit is doing very well, exceptionally well on the support vector machines, and it's also doing exceptionally well on the gradient boosting. And the red boxes are for the external validation, the blues are for the temporal validation, and you can see that there's a clear tendency that the losses, so that the losses are somewhat lower in the temporal validation compared to the external validation data, and this is just in line with our expectation. You can see that some of the methods didn't perform well when you look at logistic regression as the base machine, and then isotonic calibration, Elkan calibration, and null calibration, they performed quite poorly. And of course, we can summarize the results in this kind of figure. So in this case, the orientation has been changed by the computer. I'm sorry for that. So you can see the intercept calibration is actually outperforming everything else when you average over all machines in the temporal validation data. But you see a clear homogeneous group, and you can see that Elkan and slope calibration as well as no calibration don't perform good, and the results are relatively similar when you move on. When you move on to the external validation data, it is the same three machines that don't perform well. If we go for the mortality model, that's a completely different story. For complete restitution, we had a balanced data set, and here we have completely unbalanced data. So about 10% of the patients died during the course of the study, and 90% survived. So we truly have an unbalanced data set. There were just three variables that strike out clearly. It's age, it's the NIH stroke scale overall score, and fever. And fever, of course, is an indicator or indicator for some kind of infection that's going on in the body. And of course, this is quite bad situation. And you can see that the overall pattern looks very similarly, but this has to do with the scaling. When you look at the results from the random forest, you can see some kind of differences in the pattern. While you had two striking variables, the right arm paresis and the age here in the training data, you can see that the ranking scale shows up in the temporal validation data, and that the ranking scale and the right arm paresis show up in the external validation data. And the ranking scale clearly is non-significant in the training data. So when you just look at these different spider net plots, so the officially called radar plots, when you look at these plots here, you can expect that the results will not be that nice for these data because they are somewhat heterogeneous. And this can be nicely illustrated with this figure here, and you can see that the refit didn't perform well on the external data at all. Refit is this part down here. And it somewhat worked on the temporal validation data. And you can see that PLET calibration failed and that some other calibration methods failed when the basic machine was logistic regression, and logistic calibration was not performing good. Intercept calibration was not performing good. Slope calibration was not performing good. So we had some issues. And when you look at random forest and the support vector machines, then the pattern is definitely different. Here, the refit was actually working relatively nicely. It's the same with logistic calibration, and it's the same with intercept calibration, according to my understanding for the random forest. But as before, the support vector machine, as before meaning as before with logistic regression, the support vector machine failed here. And it's the same, it's a very similar pattern for gradient boosting and for elastic net. And when you look at some of the figures over here, some of the calibration methods didn't perform nicely. And with this, I would say at the end of the presentation, now coming to the discussion. So in summary, calibration of machine learning models is possible with a whole bunch of different approaches. It seems that logistic regression and support vector machines as machines tend to perform better on our simulation data, so on these 18 different simulation scenarios. We generally recommend logistic calibration, logistic regression, beta regression or beta calibration, logistic calibration, PLET calibration, intercept calibration formed one group. In most applications, there's one specific exception to the rule for intercept calibration, which I've touched on, but you can put them in a single class and you can choose one of these methods, and clearly we recommend logistic calibration. It's bad to do no calibration, so you should actually always think about doing and performing calibration. Slope calibration generally failed. Isotonic calibration is a bad idea, and probably this is a quite important message for the machine learning community, which is still using that. Refit failed in case of small calibration data sets, and we did not investigate the effect what happens if we have a smaller calibration data set at hand. If we have a small calibration data set at hand, then LCAN regression and intercept calibration perform quite nicely if there's no structural change in the data. And the final remark is there's still some work that needs to be done. We don't have a clear guideline. When should we keep the original model? When should we calibrate it? When should we refit it? What happens if we have unbalanced outcome data as in our mortality model? And with this, I think I'm at the end of the presentation. Thank you for listening.
Wow, that was an awesome talk. So fascinating. I really, really enjoyed it. So I will encourage all of our participants, please write in the chat or press the button to raise your hand, and I can allow you to unmute yourself if you would like to ask a question or bring up a discussion point. We already had one come in toward the beginning of your presentation, so I'll read it aloud now. It's from Eric Johnson, who says, it seems like a logistic calibration with a restricted cubic spline basis would be easy and effective. Are there any pitfalls to it that I'm not seeing?
The question is, why do you want to use a restricted cubic spline if a simple logistic calibration is doing the job? Typically, so what we've seen in our simulations is that if we do logistic calibration, then this linear coefficient is sufficient in most cases, because you just have the 0, 1 and you have your estimated probabilities, and there's typically not an awkward structure into that. So I think this would be similar to this better calibration, which actually did not outperform anything. So of course, if you do a proper model selection and you can use restricted cubic splines, and maybe you want to use silver plate splines, that's a completely different ballpark. But I don't see the need to use it, but you can clearly do it.
Great. So I have a question that is kind of relates to the work that I do. So, like you, I work in medicine, and, we're always trying to develop prediction models to, identify patients that may have certain, disease outcomes or something like that. And I think, the main goal is to incorporate it into the electronic health record so that, the predictions are made in real time. So in terms of calibration, how do you actually do that in practice? So, do you recommend developing a prediction model, calibrating it once, and then just having that as a fixed model? Or do you have to keep recalibrating it, every time you have new patient data coming in?
I really love this question, Jamie, because we have been working on a myocardial infarction project, and we actually developed the model using several machines, and we used a superlearner for the whole thing at the end of the day. And we had a calibration data set or a validation data set at hand, and so we wanted to calibrate that data set. And our idea is, if you don't have a larger sample in your hospital. So in this case, it's diagnosis of myocardial infarction in the emergency department. So if you have a whole data set available that you can rely on because you have it in your hospital information system, so electronic health record, something like this, then you can already do this calibration on this initial data set and then apply it to your patients already. So this is very similar to the setting we've used in the simulation study, where we started with the training data. Then we had one data set that we trained the calibration model on, and then we applied it to a validation data set. And in this case, we followed just this idea. So we are currently developing an app to make this model available. And in fact, either you can use our calibrated data, or you can do your own calibration and feed this into the app in a very simple way. So I think, to answer your question, no, according to my understanding, is if you have a decent validation data set at hand and have done the calibration there properly, and if you're sure that your new patients are from have the same structure, then it's not necessary to do a refit over and over and over again, so in real time. But you should think about doing a validation or calibration by hospital, and maybe you need to think about changes in when new doctors are hired, and if others are leaving the hospital, maybe they attract other patients and so on. So you might have some structural differences there.
Thank you. Okay, so here's a couple of other questions that were written in. So one person wrote, "Thank you for a great talk. This presentation mainly focused on binary outcome data. I wonder if you can briefly discuss calibration for models with survival, continuous, or categorical outcome data. What would you consider when developing a calibration method for those types of data?"
Okay, calibration continuous outcomes is definitely a bit more challenging because you have a couple of different calibration approaches available as well. And in some of my applications, I've seen that some ad hoc methods work better than some of the standard methods. That's the first thing. When you go to calibration of survival models, there is a whole bunch of recent literature on this topic. I really love what has been done there. And I can just refer you to the literature over there. One of the more challenging approaches for me is what do you do if you have ordered and unordered categorical variables, because their model fitting is hard, or let's say more challenging than this dichotomous problem here. And then calibration is becoming a mess as well. At least that's my current experience.
Great. Okay, here's another question that was written in. How the unbalanced data in the outcome variable, okay, so it's asking about how does unbalanced in your data in your outcome variable impact the calibration?
This is a really important question, and I think it's a great question, and we are asking this question ourselves. So the main point here is when we think about dichotomous outcome and we have unbalanced outcome data, then the key variable, or let's say the key statistic I'm looking at, is the events per variable. And of course, if the EPV goes down, then you have a hard time in calibrating your model. And this is what we see in our stroke data illustration. Unfortunately, I don't have a guideline right now and a good argument when do we need to be very careful with the calibration even of these models, because if you have these extremely unbalanced data, some of the machines that you use for probability estimation in the first run fail. This is what we have seen several times. Sometimes support vector machines fail. I think the illustration about the external validation data and the support vector machines were quite clear in this respect. Also logistic regression, where we had this kind of major issue with the calibration. To be honest, I don't have any answer to the question what happens in the case of unbalanced dichotomous endpoints.
Yeah, I've run into that also, even with modeling. It's always difficult when you have these challenges.
Yeah.
Okay. So again, please write in any questions. And in the meantime, I would just like to mention that our next webinar will be on July 20th at 2 p.m. And we will have one of our SLDS board members, Yelena Bradick, who's our program chair, is going to give an overview of virtual JSM and kind of highlight some of the work that is being presented by our section members. So it'll be a little JSM preview and kind of promotion for our group. We'll give it another 30 seconds, let's say, for someone to write in. But again, Dr. Ziegler, this was an amazing talk. I feel like I learned so much. It's a really important topic that I feel like not many people are talking about. So I think it's very helpful, and I'm really grateful that you gave this talk to our group today.
Thank you.
All right, well, seeing no other questions, I think we can call it a day or an evening for you over there. And again, thanks so much for joining us.
How many people actually joined that, and how many dropped out in between? Do you know?